Okay, welcome back. In this video, I just want to do some properties and examples of quotients and normal subgroups. So let's get right into it. Remember that we have defined a quotient group. So if G is a group and N is a normal subgroup, and this means that the left cosets are always the same as right cosets for that particular group. And this has to be for all the elements of G. Then we have defined an operation such that G1n times G2n is the same as G1, G2n. And we prove that if it is normal, then this actually is a well-defined operation, and this is a group. So I want to give you some examples of quotient groups to start with. So here is G is Z modulo 6. We said that every subgroup of an abelian group is normal. So if I take H to be 0, 3, for example, this is normal in G, and the quotient by H will be the cosets. There is exactly 3 cosets. In this case is H, 1 plus H, and 2 plus H. The coset H itself is the identity. And then we see that this is a group. Well, I remember like it works like 1 plus H plus 2 plus H. It is a group. This is 3 plus H, which is just H. Okay. How about 1 plus H plus 1 plus H? So it would be 1 plus H squared, or 2 times 1 plus H. This is 1 plus 1 plus H, so it is 2 plus H. So this actually tells me that 1 plus 1 is 2. So this plus itself gives me this. So this is actually a group generated by the coset 1 plus H, and therefore it is cyclic of order 3. So what we can actually get is an isomorphism, and you can define the phi that is an isomorphism. So this group is actually isomorphic to Z modulo 3. It's cyclic of order 3. What happens, there are other subgroups of Z modulo 6. So in Z modulo 6, I can also define a subgroup defined by 0, 2, and 4 modulo 6. That is a subgroup, which also will be normal because G is abelian. What is G modulo H in this case? That is Z modulo 6 quotient by the 0, 2, 4. There is precisely 2 cosets now. There is H and there is 1 plus H. So there's 2 cosets, H being the identity. So this is just going to be the subgroup generated by 1 plus H once again, actually. And this is just cyclic of order 2, so it's isomorphic to Z modulo 2. Great. These are examples that are, the group itself was abelian, so those are the easy ones. Let's now switch to a non-abelian case. G is S3. My subgroup that is normal is going to be 1, 2, 3. The subgroup generated by the element 1, 2, 3. Remember that there are subgroups that are not normal, so I cannot do a quotient, but this one we proved that is normal. So what is G modulo N in this case? There is N, and there is in fact only one more coset, which is the one when we multiply by 1, 2. This is the subgroup generated by 1, 2, 3. So this is the identity 1, 2, 3, and 1, 3, 2. While this coset is the one with the elements of order 2, is 1, 2, 1, 3, 2, 3. And you see that G is actually partitioned by these 2 cosets. G has exactly, or N in G has exactly 2 cosets, so there's going to be 2 elements in this group. By the way, remember that we can actually figure out how many elements are there going to be in the quotient. Maybe I'll talk about that in a moment. I'll just say in here that this is the subgroup generated by the coset with generator 1, 2, and therefore it is also isomorphic to Z modulo 2. This is an example of a group that is non-abelian and the quotient is abelian. Okay, so if G is abelian, the quotient is abelian, but if G is non-abelian, sometimes the quotient is abelian, sometimes the quotient is not abelian. In this case, it is abelian of order 2. What I was going to say is the following remark, that we have Lagrange's theorem. Remember that the size of G modulo n of the quotient group will be the index of G over n, the index of n in G. But by Lagrange's theorem, we know that the size of G is the size of n times the index. So the index, when G is finite, will be the quotient of the two if G is finite. Okay, so in the example that we had before, S3 has order 6, N was the subgroup generated by 1, 2, 3, is a subgroup of order 3, and therefore the quotient group had to have order 6 divided by 3 exactly 2. So I can figure out how many cosets are there going to be just by looking at the size of the group and the size of the subgroup. The next example I want to give you, we're going to need some theory before I do that example. So let me go back and prove the following. This is some way to recognize when a group is normal that is a little bit more useful than the definition itself. So let n be a subgroup. Then the following are equivalent statements. One, n is normal in G, i.e. Gn is the same as Ng for all G in G. Two, G and G inverse is contained in N for all G in G. And three, G and G inverse is equal to N for all G in G. And this is the definition. And this is the statement that is going to be the easiest to prove. So we're going to prove that these three things are equivalent, but eventually what we're going to use is this because that's the easiest one of the three to use. So how are we going to prove that these are equivalent? We have to prove that this is equivalent to this, that this is equivalent to this, and this is equivalent to that. So we're going to do a circuit. We're going to prove that 1 implies 2, 2 implies 3, and that 3 implies 1. So let me start with 1 implies 2. We are assuming 1, so n is normal in G, so Gn is Ng for all G in G. And in particular, for G in G and N in N, we have that Gn is also in Ng, so it has to be N prime G for some N prime in N. And therefore, G and G inverse is N prime in N, and that implies that G and G inverse is contained in N. And since this was for any G and any N, this says that G and G inverse is contained in N, which is what I wanted to prove for part 2. Now let's prove that 2 implies 3. So let's assume that G and G inverse is contained in N for all G in G. And then let's prove that actually I have an equality. So what I need for the equality is that N is actually contained in G and G inverse. So for n, in n, I want to prove this containment that is in here. So what I'm going to write is that, well, I do have that G inverse and G is the same as G inverse and G inverse inverse. But I am assuming this containment, so this with G replaced by G inverse tells me that this is contained in N, because this is true for any G. So in particular for G inverse, this has to be in N. So it has to be some N prime in N, and therefore N, well, G inverse N G is some N prime, and therefore if I multiply on the right by G inverse and on the left by G, I get that N is G N prime G inverse, which is N G N G inverse, and therefore since little n was arbitrary, this tells me that n is contained in G and G inverse, which is what I wanted to prove. Last, I need to prove that 3 implies 1. So now we are going to assume that G and G inverse is always equal to n, and we want to prove that Gn is always equal to Ng. First, for any n in n, we have that G and G inverse is in n, so it's equal to some n prime for some n prime in n, and that implies that Gn is the same as n prime G, and what that it tells me is that Gn, because n little n was arbitrary, Gn is always contained in Ng. And now similarly, I can start, I can go in the other direction. Also, I have that, so now what I would like is, I'm going to start with G inverse and G, that is the same as G inverse and G inverse inverse, and therefore by my assumption that has to be an element of n, and that tells me then that Ng is Gn prime, and this tells me that Ng is contained in Gn, and therefore I have both containments, which imply that Gn is equal to Ng, which is what I wanted to prove. Okay, so to prove that something is normal, it's sufficient to, so to prove that a subgroup is normal is sufficient to prove this containment, that G and G inverse is always contained in N. And I'm going to use that right now to prove the normality of a subgroup. So here is the example I want to discuss now is the following. My group is going to be the dihedral group, Dn. Remember that that is generated by R and S. R to the n is 1, S to the 2 is 1, and SRS inverse is R inverse. Okay, and the group that I want to prove is normal, the subgroup that I want to prove is normal is the subgroup generated by R. So that is the identity R squared up to R to the n minus 1, because R has order n. I want to prove that n is normal in the dihedral group. So how so? First, let's see that if I multiply by any power r to the k times n, what do I get? I'm going to get r to the k, r to the k plus 1, r to the k plus 2, up to r to the n minus 1 plus k. But at some point, I'm going to hit somewhere in here is r to the n, and there would be the identity, and then would be, or r to the n minus 1, really. And then I would get r to the n, and then r, and so on. So this is just the group itself. And I get the same thing if I multiply. On the right is exactly the same group. So that is given. Now, what happens with S? What happens with Sn? I want to prove to you that Sn is the same as Ns. But what we saw is that it actually is enough to prove that Sn S inverse is contained in N. Okay, but S inverse is itself, so this is the same as S is contained in N. But now notice that S times anything in N, power times S, that is the same as R to the minus K. This we've done a couple times, that because SRS is R inverse, that implies if you multiply, for example, SRS times SRS, that will be R inverse, which is R to the minus 2. Let me write it a little bigger. R to the minus 2. But this, when you multiply, because the s's cancel out, I get SR2S. And it keeps going. SR to the K, S is R to the minus K. But R to the minus K is certainly R to the N minus K, and that is in N. And that implies that S and S is contained in N. And we've just seen that this is actually equivalent to this, so it is it works the same way. And similarly, now if I want to do any RKSN, we've just seen that Sn is the same as Ns, so R to the K Sn is the same as R to the K Ns. We've also seen that R to the Kn is N to the RK, and N times RK. So now we see that it also works, that the cosets are the same. The left and the right cosets are the same. And therefore, with all the work before, and this implies that N is indeed normal in the end. Okay. Okay. So what is the quotient of dn by this subgroup generated by R? Well, first of all, how many elements are there? Remember that the number of elements will be the index, but the index is the number of elements in the n divided by the number of elements in the subgroup. The number of elements in the n is 2n, and the number of elements in R, because R is order n, is n, so it has exactly 2 elements. This has 2 subgroups, N and also Sn is exactly the two cosets. So it is just generated by one coset of order 2. So it is a group isomorphic to Z modulo 2. And the operation is just Sn times Sn is S square n, which is just n. So you can see that it is, in fact, an element of order 2. So the quotient, again, of a non-abelian group, Dn, of the dihedral group, by this element, I get a subgroup of order 2. So the quotient of a non-abelian group by some normal subgroup, once again, I get some abelian group. This is not always the case, but it can happen. Okay, so if you want an example let me give you an example. You can prove this. Prove the following. So let G be S3 cross Z modulo 2Z. Then the subgroup that is just the identity NS3 and A modulo 2 for A 0 or 1. This is in fact normal. So you can prove that N is normal in G, and that G modulo N, it is in fact isomorphic to S3. So here is an example of a group that is non-abelian, because this is non-abelian, and its quotient is also non-abelian. Okay, so you can prove this. I'll leave this as an exercise. Now, the last example I want to give you today is the following. So let's start with G being the integers. We can do quotients of infinite groups also. And this is an infinite group, but it's abelian. So any subgroup, remember that the subgroups, we prove that the subgroups of a cyclic group are cyclic, and the subgroups of the integers are generated by one element. So n times z is a subgroup, and is normal in G. So I want to figure out what is the quotient. Then what is the quotient of the integers modulo n? Well, it is in fact the integers modulo this subgroup. You can see the notation already tells you what it's going to be. It's z modulo n. In this incarnation of z modulo n, it is the quotient, so it is cosets. So it will be the coset of 0, the coset of 1, and the coset of how many elements are there that are different, how many cosets are there that are different, is up to n minus 1 is different, and then you can in fact prove that those are all the cosets of the subgroup nz. Here n is some integer, let's say bigger than 2. And those are precisely the elements. And in the addition of those cosets, A plus NZ plus B plus NZ will be, as we've defined the addition of cosets, it will be that one, except that, so it fits into one of those, will be the same as the class of A plus B modulo n plus nz. So you can see that this is, in fact, this G modulo n is isomorphic to the usual Z modulo nz, which we've usually worked with it as 0, 1, 2, up to n minus 1 modulo n. So that is where this notation comes from for Z modulo nz, is that it's the quotient group of the integers modulo a subgroup, which is normal, and it gives me cosets, and each one of those cosets are the congruence classes. This is what we usually call the class of 0 modulo n. This is what we usually call the class of 1 modulo n, etc. And the congruence classes are precisely the cosets of this group in this group. And there are n of them, and this is the quotient group. This is an example of a quotient group or an infinite group by an infinite subgroup, but the quotient is finite. But you can also have a quotient of an infinite group by an infinite group and get a infinite group or something of the sort. For example, let me give you an example where G is going to be the real numbers under addition, the real numbers under multiplication. So the non-zero real numbers under multiplication, let me do. And this is an abelian group. I'm going to get a subgroup. Plus and minus 1 under multiplication is a subgroup of R star. This is the non-zero reals. This is a subgroup, and it is normal. And the quotient, what is it going to be? The quotient is just the real numbers, non-zero real numbers up to sign. So the cosets are going to be basically given by the absolute value of a real number. So these are going to be real numbers modulo the identification that A is the same as minus A in the real line. Okay, so this is an example of an infinite group, a finite subgroup, and the quotient is infinite again. If you want, we can actually make an isomorphism to the real positives under multiplication. So those are, that is a quotient group. The quotient group of the real, the non-zero reals modulo plus minus 1 gives you something that is isomorphic to the positive reals as a multiplicative group. Okay, so that is all I had no, I have one more thing. Let me just give you one definition, one more type of group which has to do with normal subgroups. So a group G is simple if it does not have any non-trivial normal subgroups. There are always, so there is no other ones. If you have a normal subgroup of G, then N has to be one of the trivial ones. N is E or N is all of G. So why this definition? This definition comes about because whenever I have a normal subgroup, I can do a quotient, and that means that it is possible um, that G comes about as whatever this group is, direct product with N or something of the sort. There's going to be some other type of constructions that could be that if I have a normal subgroup, that G itself comes from other older subgroups or smaller subgroups as a direct product or a semi-direct product or something of the sort. So there might be options to reconstruct G out of other smaller subgroups. But if there is no normal subgroups, then G cannot come from something like this at all, and therefore G is a new group. So these simple groups are groups that are irreducible in some sense, and they are groups that should be essentially new groups. What are some examples of simple groups? So for example, well, let me start with a non-example. Z modulo 6 is not simple. Because we do have, for example, that 0,3 is normal and non-trivial. And we do know that Z modulo 6 is actually isomorphic to Z modulo 2 cross Z modulo 3. And it is true, though, that the quotient of this subgroup is isomorphic to this one. So this may be what's happening, that it is not normal, it is not simple, and in fact, the quotient appears in some sort of like direct product factorization of Z modulo 6. There are other groups, though, that are simple. So, for example, Z modulo P Z with P prime is an infinite family of simple groups because the only subgroups are 0 and Z modulo P. There is no other subgroups of Z modulo P, so there is no other non-trivial normal subgroups. So these are an infinite family of simple groups. And the last thing I want to say is the following theorem, and it's that AN, the alternating subgroup, is simple for n bigger or equal to 5. I'm not going to prove that here, but that the proof is in the book. We are following the book by Judson and Abstract Algebra, for example. You can find the proof of this theorem. So that gives you two infinite families of subgroups or groups, Z modulo P, or all the ANs that are simple groups. And those are some of the families that we know of simple groups. And this was a big part of the mathematics of the 20th century, is that there was a classification, a full classification of simple groups was proved, and it consists of several infinite families, such as Z modulo P for P prime and the AN for n bigger or equal to 5. And then there's also some other groups that are not part of the families, which are called the sporadic groups. And the largest one of the sporadic groups, of those groups that are simple and not in any of these families, is something that is called the monster group, which is a gigantic group, a very, very large group that is known to be simple and is the largest one, as I said, of these sort of like called sporadic groups. So if you want to read more about the monster group, that is a very fascinating topic. It has connections with all sorts of other areas, like number theory and complex analysis, and it's just like a very, very interesting subject on its own. Okay, so I'll stop there, and next time we're going to talk about homomorphisms.